Hello and welcome to video number 5 on our series of the Cavendish experiments, and today we're looking more closely at the pendulum oscillation. Now if you recall, this has been plaguing me since the Foucault pendulum days, when we noticed our pendulum oscillates left and right. So what we've come up with is gradually our experiments are proving that using our optical fibre cable, we have now produced a very, very sensitive suspension device, very, very low friction, that allows the pendulum to swing left and right with greatest of ease. In fact, I believe I cannot measure within the first probably millimetre of the swing any friction at all. So somehow we've created this frictionless suspension system by accident, or perhaps not. Perhaps someone else has beaten us to it. What I found was that when I'm using that small blue optical fibre cable, the actual pendulum will rotate almost 360 degrees back and forth, and takes at least 20 to 30, possibly more, 40 minutes to come back and settle after it's done its oscillation. So there is very little dampening from friction. And then we found that, or I've found that once the pendulum reaches its equilibrium, it just sits there oscillating back and forth a minute amount, and if we project that minute amount 8.5 metres away onto a wall, we notice that it seems to be oscillating across the central point equidistant of around about 2 to 3 millimetres, constant across the centre line. Now this is quite a controversial factor in a lot of experiments, because a lot of experiments ignore this oscillation. Now the Cavendish experiment, however, doesn't, which brings us up to another interesting conundrum. So we need more investigation. So today's experiment will be focusing on, like I said, the oscillation, and I'll be approaching it more of a flat earth point of view. So you guys, you flat earthers will love this, and seriously, there will be no Artemis anti-gravity soft toys will be affected or hurt in this experiment. Right, so why use this suspension cable? I pondered this. I can't come up with a reason. To me, it introduces such complexity, it increases the cost, just the time used to settle these pendulums, to settle them, it takes hours out of a day. And the slightest bump or interruption from a wind or a door opening or anything, and the experiment has to start again. So why did Cavendish go to the suspension cable concept? Did he know something we didn't, or was he looking for something else we didn't know? Or was he trying to hide something? And I believe there's some inconsistency with all this, and I think it actually goes back, it could even go back as far as Galileo with his experiments with pendulums. But certainly there's something suspicious with Michel. Now, we never seen his experiment, but I believe he was looking to detect whether the Earth was spinning or not. And if he was to use suspension cable, that's where the trick is. If the Earth is spinning, it should show up as this consideration. I'll just quickly go through that. What we've noticed is that the laser on our pendulum, on the pendulum plane 4, it oscillates clearly across a central point, back and forth equidistant, roughly 2 or 3 centimetres, but it's equal, so A equals B. Now what this experiment is about is to drive the pendulum this time around and in a 33-hour rotation, which it takes 33 hours to do a complete rotation. Now what I'm looking for and what I'm trying to see is, I believe if the Earth was rotating, and we're trying to simulate that now, what we should see is a bias torque on the optical fibre cable that would create, in the clockwise motion, we would expect to see the oscillation on A, the size of A would be smaller than the return path of B. So what we expect is, as the pendulum rotated, the light beam would go around one step this direction, probably 5 steps this direction because it's going in the same direction as the Earth, and then come back to 1 step this side, or 2 steps or something, back longer, shorter, longer, shorter, some sort of sawtooth. That's what I'm trying to look for. That's how I would expect to see the laser perform on a rotating Earth. However, we see the opposite. What we see is equidistance across the centre line. So let's go now to that experiment and I'll show you the setup, and we'll get into the experiment now. So quickly I'll just show you the comparison I'm trying to draw. The complexities with this swinging pendulum concept, or which Cavendish uses, the torsion. He tried to measure the torsion in this swinging bar setup, which we're sort of almost reducing here. Just the slightest bump on this pendulum, and this thing will take possibly an hour to settle down, just from that bump. Whereas if he'd used the concept of the point I have here with the ball bearing and the end of a pen tip, obviously he wouldn't have had a ball bearing tip, but he could have used a very sharp point and a dual movement to stimulate this low friction. Now just compare that to the same bump. That's the same bump on the torsion bar friction setup. Settles down within a few seconds. Now we have a friction based measurement now to measure little g, or little g, sorry, yeah. And as you can see in my early videos, you see me demonstrate trying to measure that, which I believe I can. That can be measured, that deflection. But no, Cavendish chose to use this extremely hard to measure torsion within this. This can't be measured, that first millimetre cannot be measured. That cannot be measured, that bit there. You've got no idea the small amount of energy I'm putting into this to deflect that. I'm amazed that it's been reproduced so many times and everyone goes back to it and it's sort of the standard, whereas this system here, friction determined, easily determined by measurements with simple gram measuring tools. I don't know. Okay. Alright, now I'll just quickly show you now the top, the motor drive setup. It'll be exactly the same as this, and you can go back to those early videos showing the turning the Earth around. So here we go. I'll just climb up on my ladder. So there we have it. The clockwork mechanism driving a tooth belt and precision bearing that decouples the motor from the bearing, gives a bit more decoupling, and a little switch to turn the power off Bit unsteady up here on the ladder, but I think you get the picture. Alright, here we are. At time is 0921. Humidity is 77.2 and the temperature is 20 degrees. And we're observing the motion of the laser now without the motor driving it. Alright, so we've gone to 1 centimetre over the black line to the left. One centimetre to the right, back again, 1 centimetre almost, going a bit further this time to the right, 1.5 centimetres I guess, back again. Okay, this looks like a cycle that might be a bit more aggressive. Almost 2 centimetres to the left. More aggressively going back to the right. So I guess it looks like that's 22 on the numbers there, 23, 24, okay, looking at I can guess we say that a 4 centimetre or 40 millimetre swing oscillation. And I seem to have that black line nearly centred of the cycle. Okay, here's something strange coming up. No. Didn't quite. Strange cycle, that one. Let's keep going one more time. Just monitor a bit longer. We've been monitoring for about 5 minutes. It's so the laser was taken to this position under load through the motor, and I switched the motor off, so the gears and everything would be torqued. So they're under torque, a constant torque. there's no backlash in this setup anyway, very little backlash because of the toothed belt and the toothed cogs driving it. Alright, I think that's enough. I'll go now back and turn the motor on and we'll start seeing the clockwise procession, and let's see what our swing is then. Okay, one more. Oops. No, it looks like that's 40 millimeters swing. Okay, let's switch the motor on and simulate the earth spinning. Now it's at 8.5 meters away, so I have to walk very gently without disturbing the pendulum and creating any air currents. No, okay, that looks like, ooh, it was a little bit longer. I stood up then, I don't know whether that, no, okay. Alright, walking back now to the pendulum, 8.5 meters. Very gently. Very gently. Activating the motor now. Walking back. Okay, I'm back. The cycle appeared to be the same as we've been observing. 2 centimeters to the left and 2 centimeters to the right. Alright, I think I can see a slight creep to the right. Which you would expect. We would expect it not to go as far to the left. Okay, that one didn't go. Right, I think we can safely say now that the torsion is on the optical fibre from the motor. Just give it a bit more time to settle in. Okay, that one is definitely a stronger movement to the right. I'd say that's on the 28 mark. 28.5. Going back now. This is what we want to see, how far it goes back. To the left. Alright, looked like that was 1. Not even 1. Alright. Okay, so here we go. To 31. Almost 31. Back to the left. Okay, only I'd say that's a 1 again. It's not getting the 2 steps to the left as it was before. Okay. What I'll do is I'll have to reposition that black line to give us a better reference, I think. Because these next measurements now, we're starting to, the tension on the optical cable would have settled down now from the load of the motor. So what we do now is, and the laser is going to encroach towards my setup here with the tripod, so I'll just have to shuffle things a bit. I'll get a time stamp there. Now I'm going to have to move everything across. Alright, now I moved it. The moment I see that touch the black line, okay, there we are. 1 to the right, 2 to the right, 3 to the right, 4 to the right, 5 to the right, 5.5, almost 6 to the right, how many to the left? Okay, it's gone crazy here. It's one of those weird cycles I experience. Okay, it's one to the left, Okay, there we are, left, right, there. It's going back to the left. Maybe it seems to be stopping sort of now. Can't make up its mind what it's doing. I'm guessing there's a fair bit of residual settling in that optical cable. It's definitely a different behaviour. So okay, we've gone to the right now. Let's do a surround measurement here. That's 1 to the left. 2 to the left. Back. 1. 2. 3. 4. 5. 6. Okay. Look, I think we can clearly see that there's the ratio going left to right is smaller, so on a spinning Earth you would expect to see that. You would expect to see that, wouldn't you? And that's what I'm always sort of been plagued with. I can never understand. I would think, let's see if we can grab some more data. Okay, that's a definite 1 to the right. 2 to the right. 3 to the right. 3, almost 3, going back. Yeah, okay, look, to me that was, unless someone can come up with an explanation, but that's what I would expect to see on a spinning Earth with almost a frictionless setup. You would see this bias swing to, you would notice the right movement more than the left. Alright, so I think the next thing to do is obviously reverse the motor and go to the anti-clockwise. Okay, just get a timestamp. Should have a timestamp on the timestamp on the computer, video stamp from the YouTube clip. The camera just went off for some unknown reason there. I'm back. One, two, three, four. Okay, that went 4 to the right, 2 to the right, 3 to the right, okay, what I'll do is this camera's overheating, so I think there's still residual clockwise momentum there. So I'll come back in another 15 minutes, just see what this thing is doing. Yeah, that's definitely a symmetrical . Yeah. 2 to the left and 2 to the right. Alright, I'll come back in 15. Alright, we're back here now. It's 10:20 in the morning. It's been at least 30 minutes, I guess. And a bit of surprise is our laser has swung back to the left and settled 1, 2, 3, 4, 5, 6, 7, 8, something like 8 centimetres away. It's sprung back to the left, so obviously that there was a torsion in the setup. I've just centred that, but I think it's just oscillating across back to where it was again. Yeah, roughly that two to the left and two to the right thing, isn't it? How it was. But interesting, I didn't realise that before. I haven't actually witnessed that. One, almost two to the right, back. Exactly how we observed and when we initially set up without the motor. Alright, so obviously that motor does apply a slight amount of torque, even though it's insignificant. It was enough to spring the whole system back to that left. Alright, we'll sum up now and meet you at the whiteboard. So basically the next stage will be to obviously make the background move with the dot, with the laser. So you know, we're actually getting the same velocity at the far end that I'm measuring at, but I don't want to do that till I've actually reversed the motor and gone against the natural direction of the Earth here in the southern hemisphere. But initial results do seem to show that the pendulum, or the light laser, is tracking somewhat more to the right than it is to the left on this early experiment. Okay, I think that's enough. We'll stay tuned for when I reverse the motor in the next video. Thanks for watching.